Hello, everyone. Looks like we have our participants filing in now that we've started the webinar. You are in the Internet of Water P2P Network webinar series. I hope this is where you were trying to get to today. Today, for our June webinar, we're going to be having a presentation on the Hydro Network Linked Data Index. So this will be all about connecting water data to the hydrographic network. So welcome. My name is Lucas Stevens. I'm a policy associate at the Internet of Water. And I am your host for today's webinar. So I'll be giving a brief introduction and then handing it off to Dave Blodgett of USGS, who is really the expert behind the NLDI. And we'll get into the details of these new tools that enable water data to be more accessible and more discoverable and linked to the broader hydrographic network. But first, I want to go over some brief housekeeping details. So if you have to leave in the middle of the webinar, fear not. The webinar is being recorded and will be sent out to all the registrants. And we will also make the slides available on our website. So that we will send out links to the slides and to the recording after the webinar is over. Following the webinar, we'll have a brief Q&A, and Dave will be available to give tutorials of some of the tools and some of the options available that I'll be presenting on. So please submit your questions into the Q&A box. There is also a chat box if you're having technical difficulties or any sort of problems with the webinar. You can put those in the chat and we'll try to get those fixed during the presentation. So with that, I'm going to go ahead and stop sharing and turn it over to Dave Blodgett. He can begin his presentation on the NLDI.
All right. Thank you, Lucas, and thanks for coming along, everybody. So I'm Dave Blodgett. I'm an EDGE civil engineer, kind of a research civil engineer with the U.S. Geological Survey's water mission area. I sit in an integrated modeling and prediction division, and my work spans kind of integrated data for modeling applications at the national scale to kind of data integration and data delivery in the web context. So take part in a lot of different activities from software development and data management to standards development and governance of kind of community organizations. I sit on the Open Geospatial Consortium's architecture board. I work in our National Hydrography Infrastructure, our National Hydrography Infrastructure the steering committee management group as kind of a technical lead. So I kind of play in a lot of different parts of the federal kind of hydroinformatics sphere, and I'm really excited to get to share some background with you on some of the work we've been doing kind of in the hydroinformatics standardization space to support linking data to the hydrographic network. As we get into this presentation, we'll get into some more specific tools and applications that you may be able to use in your day-to-day, and hopefully you all find this interesting. So I'm just going to jump in and say thank you for filling out the little survey before you came along. This is a little summary of 3 of the questions, just to give. This was really nice for me to see kind of who you all are and who I'm speaking to, and kind of what information may be of interest. So I'm state government folks, welcome. Really glad to have you along. I'm super excited that we're kind of starting with this Internet of Water team. We're really starting to build a cohort state and local folks, not just feds who want to work nationally. It's really, really good to see folks more regionally interested in contributing to something national. And then also just really excited to see a fairly balanced set of stakeholders here in terms of data publishers and data users. So if I'm getting into things that are not super relevant to you, I apologize. I hopefully this will all be relevant to somebody on the call. I don't want to waste your time, but I also want to cover some material that I think is important for everybody at some level. So so the second thing that I just did I read through the what are you interested in question and was like, yeah, okay, but let's look at this in a little bit of a silly way, but let's look at this. And I pulled out the top 6 words that were not really meaningful to what we're looking at here, but I liked this little word cloud. People are clearly interested in learning. I think that was that one. Yeah, learning about NHD and water, monitoring technology, sharing, all these. I like some of the words that are popping out here, as this is what this group is interested in. It was really helpful to see this. So, all right, so a little bit of pretext here. Colleague of mine that I've had some really fascinating conversations with, Ken Bagstad. These slides came from a presentation I saw of his that really resonated with me. And it's this quote that, as valuable as machine learning solutions are proving to be, they're going after the relatively low-hanging fruit. It is far from clear that this correlation-based approach is sufficient for a broader range of problems, and a different paradigm is likely to be required. So what that says to me is pattern recognition and very sophisticated techniques to make predictions based on a lot of data has a limit. And there's more nuance, there's more meaning behind some of our information than you can possibly appreciate by just using a lot of data and doing pattern recognition. And that's what we're talking about here. It's that deep knowledge network that is formed when professional, professional level, engineers and scientists come to a problem and specify things to a great degree of granularity, and make assertions that are can be reasoned over, can be used as knowledge. That's when we start to unlock some really interesting possibilities and some really powerful capabilities. So that's really, in my mind, one of the underlying goals of what I'm talking about here today is an ability to go to that next level with machine learning solutions, where these deeper kind of knowledge network kinds of tools are going to be needed. And so, just one more slide on this. This idea of bringing semantics into our knowledge systems is super key. Going kind of up the chain of more and more sophisticated machine interpretable information. Going beyond machine learning to more knowledge-based approaches is necessary. And I guess the thing I would point out is we've known this was necessary for a long time, and it's been theoretically possible for a long time. But with the maturity of the web and some of the new methods that are becoming available from the World Wide Web Consortium and others, this is becoming more and more realistic. Some of these things are still pretty pie in the sky in terms of getting broad adoption of the tool chains and the capabilities that we really need to get there. But we're in a position where the problem is technical, and it's 1 or 2 steps away rather than 4 or 5 steps away as it was just a few years ago. So, okay, so a little bit of background, some engineering research or interoperability experimentation that we did in the Open Geospatial Consortium was a project called the Environmental Linked Features Interoperability Experiment, or ELFI. And this ELFI project was basically setting out to get a handle on what kind of information should we be embedding in web pages so that Google knows that they're spatial features and that they're maybe environmental features with particular characteristics, like a stream gauge that is connected to a river or is monitoring a river, right? And the core components of this ELFI work was not specific to any one scientific or environmental science domain. It was more general to a kind of geospatial feature. And we came up with kind of two sets of information that are kind of two views of the information, the total information about a given feature. And in this case, a feature is something like a stream gauge or a well or a bridge. So these two views are rooted in a kind of a use case or a function that we would want to provide on a web page about the feature. And so we've got this idea of a preview, so a name, an image, some description, a basic geometry if you wanted to see what it looked like on a map. And then so that's the one use case, is just give me a preview of the thing. And the second use case is the network. And this network use case is easy to extend. The core of it, though, is really just topology, both in time. So say you had a storm event that you wanted to represent. It's a temporal feature that has a geospatial representation and a time that's associated with it. You might have some information about its topology in time. You may also have some information about its topology in space. But then we can extend this network use case with additional semantic systems, which would be data models. And they might be data models like, one that describes an aquifer and how it relates to other aquifers and wells, or it could be a data model about rivers and monitoring of rivers, right? And you would end up with a set of associations to other features in a system of features, which is really relevant, obviously, to rivers, because rivers and water bodies relate to each other in terms of one flowing into the next, and they make these networks that you might traverse with some kind of network navigation algorithm. So that's kind of a jumping off point. I wanted to kind of start here as this is the technical and the core background of what we need to move forward, getting information linked together on the web in a coherent system that's reasonably well documented. If we don't have these kind of two core pieces, there's not really a lot to go on. And it's important that we get these kinds of associations, these kinds of pieces of information about everything. And then we can start layering on more semantics. And one step further, and this, if this is way beyond what you're kind of ready to grok, don't worry about it. This is a little bit wonky, but it's also really relevant. A layer on top of these features, and imagine this: the boxes here are text on a web page, and the thing in the middle is what the web page is about. Now, we can layer on top of that the fact that those web pages are about real world things, things on the ground, stream gauges, wells, rivers, right? We referred to those things in the real world as non-information resources. And I often have to tell people, like, the person that you are is a non-information resource. Your email address is a identifier. It's a digital identifier that can be associated with you, right? So in the same way, we want to have non-information resources, rivers, lakes, wells, aquifers, and we want to have a way to go look them up on the internet. We want to have a way to find those things and information about those things on the internet. So that's what this scheme of resource model and content model implies. So the resource model is the thing in the real world, we have these resources that relate to each other, and we have content about those things in the real world that we want to. And so there's a set of information that we want to document the things in the real world that we care about. So I won't go into any great detail on this right now. I just wanted to kind of give you a flavor for Alfie was out about the content that we want to record about these features. Selfie, the second environmental linked features interoperability experiment, was about how do we want to retrieve that information and create network, kind of coherent network mechanisms to discover that information, catalog it, have persistence in terms of the identifiers, the URLs that we're using, so that our linked data, the information we're recording about these features, doesn't break every time we go changing a URL. Those kinds of questions were what we addressed in the second environmental linked features interoperability experiment. And if you just Google Open Geospatial Consortium Alfie, you'll find this page pretty quickly. This is the Open Geospatial GitHub.io Alfie. And I was actually gonna, while I'm on here, I believe I can chat links at you if I can find the chat. So that's the first, I guess the first kind of resource jumping off point. The Alfie and Selfie engineering reports are very approachable. I'm incredibly proud of those two pieces of work, and highly recommend if the piece of this that I just went through is kind of interesting and you'd like to learn more. They're not long, they're not hard to read, especially the kind of executive level summaries are really, really digestible. I'd really recommend going and taking a look at some of those materials. So, all right, moving on. So I'm actually, I'm not going to spend a tremendous amount of time on the Network Linked Data Index in particular. I'm going to spend a lot more time talking around the edges of it, so you can kind of understand the context for the Network Linked Data Index. And once you understand that context, I think understanding the system will be pretty straightforward. So, but let's talk about it for a second. What is the Network Linked Data Index? At the core of it, it's a search engine, but it's a search engine for data associated with a hydrologic network. And so in that context, it can index new data. We can go out nightly and crawl some data source and pull it in and add it to the index. And it provides search services. So you can come in and say, I'm interested in stream gauges upstream of that stream gauge. Ta-da, right? You can say, I want the drainage basin boundary upstream of this network location. And that gets to the second point here. It's a set of services capable of returning custom hydrologic features. So it can do network navigation, it can return basin boundaries, it can do kind of downslope trace paths and cross sections as we go forward. That's some functionality we're kind of in the process of releasing to production now. And so it kind of serves this dual purpose. It's able to provide you in a sense, it's able to provide you the index itself. So the index that we use under the covers is the stream network, basin boundaries, elevation data. So it's able to return information about its internal index and the geometry of its internal index. But it can also return information that's associated with that index. There's some real power to that. So we can use the same API to return. So we can use the same basic methods to return either views of the network, the index, or the data that we've associated with the index, stream gauges, et cetera, right? So at the end of the day, it's really I shouldn't say just, but it's really just a convenience API. So it's a programming interface that provides some convenient functionality over a set of both networked hydrologic features and data that we can relate to those features. And so here's its kind of design componentry. So I've got data sources up here as a lumpy box or a lumpy cloud, because these data sources are all ostensibly web resources. They're in the cloud. They're on some server somewhere. They're not necessarily close to the NLDI in a network sense. And then we've got client software, which could be quite diverse. It should be quite diverse. We've already got quite a few clients. I saw a few of the people that were going to be on this webinar use the NLDI to some extent, or maybe write clients for it. And so this is kind of out in the internet. We don't necessarily, these things are not necessarily tightly bound to the network linked data index system itself. And then so we have the idea of crawlers. And there's currently 2 implementations that are supported by the system. The number of crawler implementations should grow over time. We can get a lot of mileage out of what we have now, which is just what catchment is a point in. So do a simple point in polygon index, and then if locations have a reach code and a measure, so the kind of network reference for where a point is on the NHD plus network or the NHD network, it can just index that information directly. So those are the 2 crawler methods that are implemented currently. But the idea is we could have a diversity of crawler methods here that you could choose from. So the crawler is able to go out to a data source, pull down information that's been registered, and incorporate that into the NHD plus feature and index data database, right? And then there's an NLDI API that can feed or read out of this database and provide the search service and the kind of convenience API that I was talking about a second ago. And then the thing that we're working on right now that's going to be coming out soon, in the next few months, is a geoprocessing API that kind of sits alongside the NLDI to do things like splitting catchments to precise locations. Say you wanted a drainage basin boundary to a very particular place, not just the nearest NHD plus catchment. It'll do that. It'll do a downslope trace if you wanted to get kind of a raindrop. Some people call it a raindrop trace down to the nearest intersection with the stream network. It'll do that. And so far this geoprocessing API supports functions that require access to elevation data, where the core NLDI API is just working against a database. And there's performance reasons for that. The elevation data just takes time to work with. It's much larger, and optimizations are much more difficult. Where with direct access to an indexed database, we can have kind of really fast, really efficient functionality coming out of our core API. So as we go forward, the relationship between these 2 is going to evolve. The NLDI API will likely call the geoprocessing API for some things, and that's kind of a work in progress, and we'll see where that goes. So that's that piece. And so coming back to, I glossed over this selfie and Elfie stuff in terms of real nitty-gritty details. I could spend 2 hours going through that material alone. But this diagram describes how the network linked data index exists in the context of different kind of types of URLs or different types of web resources. And so a web resource is just something that can be retrieved from a URL, a uniform resource locator. And so there's a system that I'll talk a little bit more about later on, or we can get into in the question and answer time, called geoconnects.us, that's providing a service very much like the digital object identifier service, in that geoconnects.us provides a persistent URL that redirects from the geoconnects.us root domain to some other domain that it knows about. So like with a digital object identifier, you go to a DOI resolver URL and you get forwarded on to Elsevier or whoever it is, Elsevier, I never know how to pronounce that. But the point being, we have a system of persistent identifiers and a system of redirects that allow systems like the network linked data index and other kind of linked data infrastructure to rely on persistent URLs rather than needing to update linked data constantly. And then so the NLDI should be able to rely on these persistent kind of redirect URLs that redirect to information about environmental features and monitoring features. And then from there, we can get to time series and other data that's been collected at or collected about these environmental and monitoring features. So this is just kind of a network diagram of how this should all work. It's a little bit different view, but I think this does a nice job of showing how we really want to stitch all this together. And each one of these boxes has a tremendous amount of complexity that we can dig into. But at a very high level, I think this is a nice way to kind of break down functionally how this all works and show that we're working on the network linked data index in the context of a persistence kind of redirection service, a set of environmental and monitoring features that are integrated and connected to each other. And then all that kind of dives off into time series and other data for kind of core data access. Okay, so come up for air for a second and switch gears just a little bit. And get into, so this is the beginning of a set of slides or a set of information about a data model called HyFeatures. And the beginnings of the network linked data index were when I was finishing up and getting HyFeatures published. So HyFeatures it's a conceptual data model published through the Open Geospatial Consortium. And it's intended to provide a set of concepts to document surface hydrology features. And to appropriately introduce you to HyFeatures, I have to kind of have a little bit of a general lead in here. And that's that when we're looking at a hydroinformatics problem or an informatics problem where there's a spatial component, we can decompose the problem, or we can decompose the information we're working with in two ways. We can use kind of a spatial decomposition, which, I mean, counties are a spatial decomposition of a state, right? States are a spatial decomposition of a country. Watersheds are a spatial decomposition of the hydrologic landscape. So we can decompose the problem spatially, right? We can also decompose a problem in a kind of modeling concept way, where we say, you know, we're going to look at the surface water contributing component of a watershed separate from the subsurface water contributing component of a watershed. Or we're going to look at the overland flow and hydrodynamics of a watershed separate from the runoff generation component of a watershed, right? And that kind of concept decomposition is a really powerful thing if we want to kind of divide and conquer the overall problem and define these interfaces so we can have like a simple representation here that interacts in a coherent way with this other simple representation over here, and we don't actually have to solve a whole problem at the same time. So HyFeatures uses this dual composition or dual decomposition method to break up hydrologic landscapes, and it aims to provide this kind of network decomposition of catchments and flow paths, and then a kind of what we're calling a realization decomposition of the idea of a hydrologic unit, a catchment, right? So that's the first thing. You just have to. It's a little bit of a brain bender, but I think most hydrologic kind of people that are trained in hydrology can get this breaking the hydrologic function of a piece of land apart into hydrodynamics and hydrologic characteristics. That's really the core of it. And then the spatial is pretty straightforward. So the second thing here is if you're not familiar with this term class in the context of software development or kind of information modeling, it's really critical to most data models. And that's that's basically because most data models are defined as class models. So in this context, class comes from the UML paradigm, the uniform modeling language, and it's a visual language for expressing types of well, it's used for a lot of things in information modeling and software, but it's a nice formalism for information modeling. And so a class is a set or category of things having some property or attribute in common and differentiated from others by kind, type, or quality. And it's very specific. Some of these terms are a set or category, kind, type, or quality. These are very kind of defining. They allow you to say this is one of those or this is one of those with specificity and a lot of detail. So that's what HyFeatures is all about. Okay, so this is the spatial and network kind of decomposition model that HyFeatures uses. And so we call this the catchment model. And it should be fairly familiar. The idea that basically the landscape is made up of catchments. The catchments contribute or have an outflow to what in the data models called a hydronexus, and they get inflow from a hydronexus. So this is an HD plus data model, essentially, right? You've got catchments and nodes. There's nothing too groundbreaking there. And then so a catchment, so the kind of cool thing about catchments is they can be catchment aggregates. So this open arrow is a subclass relationship. So we're saying that a catchment aggregate is a type of or is a subclass of a catchment, right? And then we've got a couple of other types. We've got a dendritic catchment, which is a catchment that has one and only one outflow. And we've got interior catchments or catchments that don't have outflows, right? And so a catchment aggregate is an aggregate of dendritic catchments and interior catchments. It's straightforward, right? But this is it's simple, it's stated, and it's recognizable, but it needs to be specific. If going back to the kind of first couple slides, computers are going to understand it, and we're going to be able to use it in kind of AI type workflows. So this is why this level of specificity is needed. But these are very generic things. We could realize these in different ways. We could create physical data models to represent these things in many different ways. So the next, I guess, the last thing I'll point out here is there's an association between this very general catchment and how it has networks of catchments, and it can be made up of many other catchments and that kind of thing, and this idea of catchment realization. So that gets to the second kind of decomposition I was talking about, this kind of functional decomposition, or what's the word I was using? Model concept domain decomposition. So a given catchment might have this 0 to many catchment realizations. And I'm not going to go into much detail there, but if you want to learn more about that idea, I guess I would encourage you to kind of spend some time with the HyFeatures specification. And there's some really interesting work going on right now in the next generation national water model that's being worked on among the kind of Office of Water Prediction, National Weather Service, and partners. And if you look that up, there's a GitHub repository with a pretty nice recording that's on YouTube about kind of how the core of the next generation national water model is going to use this catchment concept, and then catchment realizations are essentially the types of software that makes up the system of models to predict the function of a catchment and how it interacts with a network of catchments. So. Okay, so the next detail of HyFeatures I want to go into is how it handles indirect position or hydrolocation. So this, what we're looking at now, so we're on, in this diagram, we have catchments and nexuses. And remember, I kind of reiterate, we're talking about classes here. So each of these boxes is a set or category of things having some property or attribute in common, differentiated from others by kind, type, or quality. So in this diagram, we have this hydronexus HY catchment and this basic system of inflows and outflows that form networks. Okay, so we have that same pairing here. But what we're adding, what we're looking at now is that a hydronexus is realized by a nexus realization, which is a hydrolocation. And a hydrolocation is really just some geospatial entity. It's a location. This is typically going to be a point, but it doesn't have to be. It could have some geometry. And it has a type. So we see this hydrolocation type list here is, you know, this kind of typical list of things: hydrometric station, stream gauge, a rapids, river mouth, sinkhole, et cetera, right? There's a whole bunch of different types that could be hydrolocations. Confluence is a super typical one. But then this hydrolocation is how we associate different data sets to each other. The hydrolocation is how we index data to the hydrologic network. And so this separate diagram down at the bottom here is showing, now we've dropped the catchment out and we're just looking at hydronexus, hydrolocation, and indirect position. And there's some details about the indirect position I want to kind of key into here. The hydrolocation has a referenced position, which is an indirect position. And the indirect position is measured along the flow path. And so, again, not groundbreaking. All we're saying is we have a point along a line, duh, right? But there's a lot of nuance there, and it's very specific. This idea of indirect position must be measured along a flow path. That means one and only one flow path, which is a geometry. It's a line, right? And if we want to be able to connect all this information to a computer system and have it be automated, this level of specificity and having kind of consistent implementation of all these specifics is really critical. So the aim of the Network Linked Data Index, the aim of a lot of the work that's going on in kind of this hydroinformatics, Internet of Water space, is to implement systems that support kind of useful profiles of this information, where we're linking hydrolocations, which could be related to watersheds and catchments, to flow paths using very specific semantics and encodings. So a couple other things I could go into there. One of the big ones is that this flow path, which I didn't, I don't have anything real detailed on right now. You'll hear more about it later. The flow path is a catchment realization. So there's a really interesting kind of almost circular set of relationships between the hydrolocation indirect position and the catchment itself. And it ends up being a little bit problematic to some people that a hydronexus doesn't have to be, so excuse me, a hydrolocation does not have to have a nexus. It does not have to be at the outlet of a catchment. A hydrolocation could be anywhere along a catchment, which is where you would associate it with the flow path, right? And there's more there that I could go into. I'll leave that for now, but the kind of leading thought is, if you were going to integrate multiple systems of catchments that don't all kind of break up at the same outlet locations, the one data set would relate to the other at hydrolocations that are along the flow paths in the other data set. So there's some interesting kind of network integrations that we can dig into here about that kind of relate multiple data sets to each other in a really clean way, not necessarily a simple way, but a clean way. Okay, so that's the kind of way in the weeds quick summary of the class diagrams that are really important here for the HyFeatures data model as it relates to indexing data to the river network. I'm going to step back, but continue talking about HyFeatures. And so this symbology that I'm about to show is something that came out of my work on the next generation national water model. And it was an attempt to kind of summarize the HyFeatures feature types, some of the core feature types, into a symbology that was theoretically kind of easy to communicate and easy to use in little diagrams. So what we're looking at right now is a catchment aggregate, right? The entire thing is a catchment aggregate. There's 2 nexuses, there's 3 water bodies, there's 3 flow paths, there's 2 nexuses that are realized by hydrologic locations, and there's one hydrologic location along the downstream flow path. So I'm going to walk through that just a little bit. So catchment area is a catchment realization that calculates a water budget and delivers flow to a drainage network. So, and that third sentence is stilted, I apologize. The point is, how we, and this is actually kind of a side comment related to hydrologic modeling and how catchment area works in a modeling context. A catchment area might be a continuous gridded representation of hydrology in a watershed. It just as well may be a statistical lumped realization that estimates runoff given rainfall. That is completely flexible and kind of beside the point. The point here is we have a type of feature that has a function, which is to calculate a water budget ostensibly and deliver flow to some drainage network, which is eventually probably gets to the outlet. The drainage network is a system of flow paths, essentially, but we also have this kind of core concept of flow path, which is a realization of the catchment, and it's a partial. It's a part of what it means to be a catchment, and that is get water from an inlet to an outlet. So there's some system of flowing bodies of water in a catchment that takes water from the inlet and gets it to the outlet. And that's part of what it means to be a catchment, right? So and flow path is that. A flow path has a relationship to a water body. And the distinction there is a flow path is 1D. A flow path is where you would attach a reference to some other data set using indirect position. A water body has width and depth and velocity and temperature and all those other attributes and characteristics. And it's a different kind of feature. It's not only a one-dimensional connection that you could use for linear referencing. And so there's actually this idea you could tie water bodies and cross sections across water bodies to a flow path using hydrolocations. That's the kind of connection there. And that's all super flexible, super complicated, things to be worked out in implementation. And that's, so there's some of that kind of implementation happening right now in the next generation national water model. So from a modeling perspective, a flow path might support hydrologic routing directly. Like if you don't actually need attributes of width and depth, et cetera, to do your routing, you might just convey flow using a flow path because that's enough. That's all you need, the connectivity. But if it's got a storage characteristics, if it's got hydrodynamic characteristics, you're jumping off into something more than flow path. And so water bodies, right, which are of type river, lake, impoundment, et cetera. So typically you're going to have aggregations of water bodies. They're going to be associated with catchments in a somewhat fluid way, pun intended. The system of water bodies needs to be decoupled from the landscape to a certain extent, obviously coupled to the landscape in some contexts as well, but it needs to be treated separately than the strict kind of here's how the flow path network works. And anyways, that goes well beyond the scope of what I should be talking about, but I just wanted to kind of put this in to be complete. Okay, so catchment and nexus are these, in HyFeatures, they're referred to as unrealized features. And that's because to realize the entire catchment, you have to do a lot of things. And to realize what it is to be a nexus, you have to do a lot of things. And down in the very, grit of it, a catchment is a it's a hydrologic, hydrodynamic, biological, soil pedological. Anyways, it's a soil system. It's an ecosystem. It's all these things, right? A nexus is a chemical mixing model and a set of momentum and energy interfaces between water bodies, and all these different things that are implied by the connection of two hydrologic systems, right? And we realize these things in various simplified ways. And that's all this is really getting at. But the tracking of identity and connectivity needs to be done at this holistic level if we're going to have interoperability down at those more detailed levels. And that's kind of the key to this slide, essentially, is look, we have this kind of holistic view so that we can have interoperability across our less holistic views. And I think this is the last of these slides. So hydrolocation is just a dot. We need a zero-dimensional feature. And the thing I point to for that need is ordering. Upstream and downstream ordering can really only be done if you are unambiguously upstream or unambiguously downstream of the other features of that kind. And you can only be unambiguously on one side or another of a line or a point. So a point it is, right? And the idea of a hydrolocation is that it is a location on a flow path that would be linked to that flow path and potentially other features like cross sections in water bodies. And whether or not the hydrolocation has an indirect position associated with it, just saying that a hydrolocation is on a flow path or that a feature is a hydrolocation, that's a lot of information, and you can make a lot of inference about what kind of associations you can make to flow paths based on just a statement of this thing is a hydrolocation, right? A well would never be a hydrolocation. You wouldn't say that a well could be associated directly to a river. It would always have to be associated through an aquifer or a shallow flow system or something, right? But a bridge could be said to be a hydrolocation, and it would be a thing you would index to a flow path using some kind of automated method. And if you knew which flow path it was on, you'd have all kinds of good information to be able to do that indexing. So that gets into one of the first kind of core pieces of information I want to have everybody walk away from this with. And that's, if nothing else, tell the world that your data is intended to be on a river. That's basically saying this thing is a hydrolocation. If it's not along a river, tell people it's not along a river. Tell people that it's a point that's of some other type, right? And then people won't go trying to index it to rivers if they listen to your declaration that this is not on a river. And that binary choice is really basic, but really important. And it's not always obvious. There are plenty of things, water quality observations, for example, that have been taken in a floodplain, right? If we don't know, unambiguously if that water quality sample was taken in the floodplain versus from the bank of the river or from the river itself, there's no automated means to make an index to a flowing body of water, right? And we need that basic piece of information. This came from a flowing body of water that was a flow path, ostensibly. And the next piece of information is what flow path. what river, right? And so we need better systems of identifiers for rivers so that we can make those assertions. But that's the other basic piece of information is what river was this hydrolocation or is this hydrolocation on? And we don't need the precise location along the flow path. We just need to know kind of an identifier that needs to be linked to, and we can go look up the location usually very easily. So, okay, so this is the kind of full symbology. I think this is useful just to kind of grapple with these concepts and understand how they work together. If it doesn't resonate, sorry, but this has worked with a few people. It works with my brain pretty well. But anyways, hopefully that was useful. I think that's pretty much the extent of my material on HyFeatures. And just thinking about time, we started at 1 and wow, time's flying. So I'll go for another 10 or 15 and we'll stop for questions. Is that good?
That sounds about right.
Okay, cool. Okay, so some work that I finished, so working with a number of colleagues from around the kind of community, been working on this. This manuscript was a slog, but it's done. It came out in environmental modeling and software late last year. I refer to it as main stems. If you search environmental modeling software main stems, actually, I'll just give you this DOI. Let me open this up once. I will put this in the chat, copy link. I'm really proud of this work. This was a lot. I have a data release coming with this that I've been working on for going on 3, maybe 4 years, depending how you look at it. It's really it's kind of the biggest thing I've done. So really proud of this. I think it's really cool. Hopefully you do too. So main stems. This is the Seine River, and this is from this is actually a drawing from the 17th century that Edwin Marriott, I think is the name, drew. And this is the earliest. This is the earliest known that I know of, and I did some pretty deep digging map that recognizes a main stem river, a headwater area, and a drainage basin boundary. And so that's how old these concepts are. And I think that's it. I think that's an interesting artifact. I think it's kind of a lot of the terminology that we use for rivers and watersheds and basins. They've been in our kind of cultural parlance for so long. They're so familiar that when we try to bring these super specific data modeling concepts to them, it feels overdone. It feels wrong in a way, because we all kind of get these concepts. But if you try to pin somebody down on precisely what a drainage basin is or what a watershed is, they kind of get wishy-washy because they're defined in multiple ways in different contexts, and it's not as simple as just one thing. But when we bring a computer in that needs to interpret data, we need some specifics. So that's essentially what we're trying to do with main stems. And all main stems is saying, really all it's saying is there's 2 important feature types here, a drainage basin and a main stem. And they relate to HyFeatures. A drainage basin is just a catchment that has some constraints, single outflow, so only one outflow, 0 upper catchments, so no inflows, or no catchments upstream, and 0 inflows, so no natural inflows of water. And so the 0 upper catchment, 0 inflow are essentially saying the same thing, but no water bodies flowing in and no upstream catchments. And then there's this idea of a primary flow path for that drainage basin. And this, this is like a cultural assertion, right? Because when you're paddling a canoe up a river, you have to decide which is the main path and which isn't. And it's an arbitrary choice.
There's a lot of different metrics you can use for what primary is, but nevertheless, we always want to choose one. There must only be one source of a river, and you have to go all the way to the top. So you got to keep making these choices, and that was a cultural choice that was rooted in naming. And I think that's a really fascinating kind of artifact of these data and what our main stem rivers are, right? It's like why does the Mississippi go to Minnesota and not Montana or wherever the true headwaters of that drainage system is? Okay, and so visually, what does this mean, right? Well, we have a drainage basin, the big boundary in the outside, and a single main stem. There's a system of catchments that makes up the kind of local drainage areas around that main stem. And each one of those catchments has a tributary that comes in at its nexus, at the nexus of that catchment, right? Each one of those has a drainage basin, and so on and so forth. So you could keep zooming in on this system until you kind of run out of geomorphic features to delineate. But there's this really core question. Where is the headwater? And this gets to we need to be able to identify main stem rivers for drainage basins to a certain degree of granularity. But when you look at multiple data sets and try to do that, it's not always clear which path should be the upstream path, right? And so what we're looking at here is, I think red is the RF1, the earliest digital representation of rivers for the US. Blue is the NHD plus V2, the medium resolution or 1 to 100K resolution hydrography from NHD plus. And in black is the NHD plus high res. And I believe the lines are essentially what that data set says is, or is the path that you would naturally choose. So the each kind of, you can follow up where they go. And it's totally undefined which one is the upstream main stem. And where would the headwater be? Like where they all come together? What about the next data set that disagrees, right? How far do we push this upstream? These are the kinds of things that I lay up at night thinking about. It's awful. So anyways, but this is a really important question. How far upstream can we push our kind of uniquely identified rivers? Because at some point, all of our data sets are going to disagree. And there does need to be a choice made about identification of rivers. And what we're going to say is the kind of canonical community recognized headwater source area. Okay, so that's the slides that I have. I now have a set of kind of materials that I want to jump off to just to give you things to go work with using the information I've conveyed to you. And I'm happy to dig into any of these in the question and answer, or we can just talk. But I'll quickly just run through what these are. So the first link here, and I'm just going to jump over to my browser and close that tab and that tab. All right, so the first link I have, and I'll just drop all these in the chat so you can go to them while we're talking. I'll clean that link up. There you go. All right, so this first one came out of the National Hydrography Infrastructure Working Group, which is a group of largely kind of federal stakeholders talking about how to go forward with the National Hydrography Dataset and its data model and all the various things we want to do with it. And so this is a conceptual model with some terminology to be used for hydrographic addressing. And it's very much rooted in the material that I've already discussed with you, but it goes a little bit more specifically into the terminology of the data sets and the practices that are common among kind of hydroscience practitioners in the US. And anyways, I won't go into great detail here, but essentially we've got a little bit of a conceptual model, some terminology, talks about how we use how we address data, what is a hydrographic address, because it's not always entirely clear what it is. A hydrographic address does not have to be a hydrologic location or hydrolocation. There's a little bit more to it than that. What information is involved. And then we've got like probably the most important or most useful piece here is we've got an inventory of existing tools and a description of what they can do and what they're like and kind of who they're useful to and all this. So this could be a very good resource for a number of you if you weren't aware of it. It hasn't been distributed very broadly, but it's also fairly new and not super duper complete. But it was kind of the best we could do with the information we had as we were working through it last year. So there's that. The next thing for the Python developers among you, I'm mostly an R developer. There's a package developed by my colleague Daniel Weifery out of the ecosystems mission area here in USGS called HydroLink. It has a collection of tools to download and index data to the NHD. So download NHD data and index data to the NHD. It's pretty well documented. It's open source. I highly recommend if you're working in Python and you want to link data to the network, HydroLink is the tool you should be looking at initially. Engage with Daniel. He's fantastic. I highly, highly, highly recommend working with this stuff. The other thing in Python, link please, absolutely. So there's that one. The other thing to be aware of in the Python ecosystem here that would work really well with this is this HyRiver package. That is there. So this is another colleague of mine, Tahir Chagini. He's put a tremendous amount of work into this. I think it pairs nicely with what Daniel's been doing. And I would leave it up to you to go through kind of documentation and demonstrations. Tahir did a little demonstration of this at the ESIP meeting that we did last week, the week before last. And I will give a link to that as well. So if you can't get enough of webinars that I've done about the NLDI, there's a similar but more demonstration-oriented webinar that was recorded last week that you can go take a look at there. Okay, so for the non-script writers among us, the Python HydroLink tool has been incorporated into a kind of web interface called the HydroLink tool. You do have to have an ArcGIS Online account, which you can get as if you can declare that you're a developer and get an ArcGIS Online account for free, I believe. So if you don't have one, there should be free and easy methods to get one. And once you've done that, then you can basically upload a shapefile of locations. This tool will walk you through indexing them to the NHD and then downloading them again as hydrolocations with indirect positions, as I was describing from HyFeatures. But in this context, we're talking about NHD events. So an event which is a reach code and a measure for the indirect position component of the hydrolocation. Okay, so link please. There's that. Then for the R developers among us, my package, the work that I've been doing, see the question there. No, to download data from the NHD Plus, I would go to Tahir Chagini's package, HyRiver. I believe that HydroLink primarily focuses on downloading just the flow line you need to index data to the river network. But I would refer you to the package documentation to get the truly correct answer for that. So my package in R is useful for downloading data from the NHD as data sets. There's a getting started vignette that shows how to do that. There's kind of a data access reference section for how to download both NHD plus v2 and NHD plus HR data. There's also a number of vignettes, so working with NHD plus HR, plotting, and indexing and referencing. So this vignette goes through how to index point locations to a river network. It shows how to index information where you might have multiple matches for a given point. And it shows how to work with water bodies where you might have points that are variously in, symbology is unfortunate there, where you might have points that are variously in or out of water bodies, and be interested in which ones are within a water body and which ones are not, or which ones are near a water body and which ones are far away. And the last thing I would mention from the NHD Plus Tools package is I've recently implemented a little more functionality for indexes that is not in the vignettes yet. And the real exciting one to me is this disambiguate flowline indexes, which allows you to get back. So when you say index, get flowline index, you can say max matches is however many within a radius. So you might get back 10 matching flow lines within a radius. And disambiguate flowline indexes allows you to pass in either a drainage area metric or some other numerical metric, or a name, a known name, right? So if you have names for your gauges and there are names on the rivers, we can run kind of a name similarity score and disambiguate which river location should be on based on that name. So that's kind of is a built-in function now that allows you to do that disambiguation, and it's really helpful, especially if you have drainage areas. That's kind of the master metric to disambiguate whether you're on the little tributary or you're on the main big river, or vice versa. You're on the little tributary rather than the big river. So that is NHD Plus Tools, and that was pretty much what I wanted to share in terms of links. I will link you to that as well. Sorry, NHD Plus Tools, and I apologize. NHD Plus Tools got kicked off of CRAN a little while ago, and I've been working diligently to get it back on CRAN, but it's currently not installable via the typical install packages. You have to use DevTools and go from GitHub. So sorry for that. If you are going to go install it, that's just kind of a side note. It should be back on CRAN as hopefully by next week, but that is that. So that's what I've got. I'd be happy to take questions. I'll maybe pop back to something a little more pleasant to look at, and we can talk.
Yeah, so we got one question here, which is sort of a policy application question for your headwaters and main stem paper and tools. So the question is, the main stem and headwaters point seems very relevant to the Waters of the United States Grand Challenge. Could this tool work to implement the reasonable nexus to navigable water rule as a threshold to identify WUCs? Could you? I know that's
thanks for that. I mean, thanks for that, Adel. That is a very interesting question, and one that I want to be careful. Anything related to WOTAs, we have to be careful. The main stems data model and how far we push a identified main stem upstream are two very different questions. The main stems data model exists regardless of how far you push them upstream. And the main stems data model is used to catalog information in terms of drainage basins and the main stem river in a drainage basin regardless. And it would be very useful for tracking waters of the United States. So this as a framework, this idea of a system of main stems. Actually, I have a nice animation that shows this really well. Right. Come on. Here. So using this idea of you've got your primary main stem, you've got your secondary rivers, your tertiary rivers, and this kind of stream level paradigm. Using this as the framework for tracking waters of the United States, because they're connected in this kind of network that forms a complete system over the landscape, makes a lot of sense. It's a different question which ones of these connections count, or which ones are truly waters of the US, or which ones are truly ephemeral or not, right? That kind of thing. But anyways, yes, very useful, but not going to answer the question in particular. It's just a nice kind of data model to support it.
Great. So if anybody else has any questions, feel free to put them in the Q&A box, or if you prefer, if you raise your hand, I can take you off mute and allow you to either make a comment or ask a question live. In the meantime, so I've got a couple of questions. So you were talking about the like the set of associations to other features, which is sort of what gets built in with all the indexing. So are these set of associations easily expandable? Is there a set number that has been already thought out completely?
I guess, do you mean types of associations or literal like features that are associated with each other?
Types of associations between features.
No, I mean that's kind of so this is an interesting nuance, or an interesting kind of challenge. We want to have very expressive data models and ontologies that allow us to make all these meaningful assertions about the things we care about, the things we want to document. But when things become too when the numbers of ways of encoding information becomes too numerous, the meaning of any one system starts to break down, starts to lose value. So it's like we want the minimum number of ways of describing the things we want to talk about, and no more.
Right.
So to answer your question, yeah, there's certainly other things that we haven't defined yet. But most likely those things have already been defined like 3 ways. And what the real challenge is at this point is to recognize that those 3 ways are the same and decide that we're going to use one of them, or we're going to define a unifying way of talking about things that allows those 3 to kind of collapse into one, right? And that's that's a challenge. That's the challenge of interoperability and building these kinds of specifications and getting them to be adopted in a way that is meaningful. So anyways, hopefully that answers the question.
Yeah, no, that's helpful. All right. So we have another question here. Do any of these tools work with the watershed boundary datasets?
Good question. So the watershed boundary dataset is an interesting case, and actually what you're looking at in this diagram is actually the watershed boundary dataset associated with the NHD Plus version 2, where we basically found the main stem collection of WBD HUC-12s for each of the main stem rivers in this network. I believe this is like the mobile. This is maybe the Atchafalaya. Anyways, I don't remember exactly what river this is. So, and that's this up here. Similarly, these are collections of HUC-12. These are collections of HUCs that have been joined together for this river system. So HUCs are catchments. They're catchment boundaries in a real sense. But they don't always have one outlet and they don't always have one inlet. So some of the tools, so I'm answering your question by basically saying yes, but HUCs don't follow the data model that we want to think that they do all the time. And when we force them to, weird things start to happen. And that's I've been working pretty hard to figure out how to get the HUCs to behave as catchments so that we can apply typical NHD plus type tools to HUCs. And it's possible. You just kind of have to force the issue and ignore the fact that there's multiple inlets and outlets in some cases. And that's not the end of the world. I mean, hydrologists are really good at abstracting away things that are inconvenient about the way the real world works and kind of just making things function the way they want it to. But yeah, so like in NHD plus tools, we have a download WBD here, and the WBD has a next down WBD attribute that implies that there's a network there. It doesn't have a linear representation, so the idea of an indirect position of a feature relative to the WBD doesn't make much sense. But you could say a feature is of type hydrologic location, which is implying that it's on a river, and you could say that it's topologically in a WBD hydrologic unit. And those two pieces of information would basically tell a person that, oh, this is a feature along the flow path that we don't have necessarily, but along the flow path of that catchment, which is a WBD unit. That's a little tenuous, but that's possible. But that's kind of the extent of it. So kind of some limitations to what you can do, and trying to lead where we might go. I think. Well, I know as we work forward with the WBD and the NHD plus, one of the kind of stated goals that's out there right now is conflation of the WBD boundaries and the NHD plus, or whatever that looks like going forward, which is an interesting concept because the WBD and its ability to aggregate into larger and larger basins with some structure, that's something you kind of can't do with the NHD plus. It's not easy to create hierarchies out of NHD plus catchments, and having a hierarchical network that resolves down to the catchment level would be really nice. So that's certainly something we're looking at and working on going forward. And that's actually kind of one of the reasons I was working on the main stems work in the first place. And like that, this here where we're integrating the NHD and the WBD, that was kind of core to why I was doing all this stuff. So anyways, probably more than you were really looking for in that question, but that's side fascination of mine, is how to force the WBD to be nice to NHD. So.
All right, great. So I'm not seeing any other further questions.
Okay.
So we'll go ahead and get ready to end it there.
Okay. I guess one other thing I would show just before we step away is if you are interested, so while we're doing this, if you are interested in contributing kind of to the community and you have data or you have ideas, you don't just want to like see what's going on the kind of development edge of things, I really encourage you to look us up at geoconnects.us. So if we go here, geoconnects.us is an Internet of Water project that I'm working on with primarily with Kyle Onda, who may or may not be on today, but this is a really good place to just kind of have an entry point to contributing and understanding kind of the big picture and what's going on. The other thing more specifically, if you're interested in the NLDI, we'll go to, no, not DB, I want crawler. So the repository for the NLDI crawlers is here. And there's actually a table here that says if you wanted to contribute hydrologic locations to the NLDI, this is the information that we need and some basically some information about how to contribute to the NLDI is here, and that would be the place to start. And typically we would see a contribution to both geoconnects.us, or ideally we would see a contribution to geoconnects.us and then to the NLDI, because the feature URI that we get in the NLDI ideally is actually a geoconnects.us persistent identifier. So if you're interested in contributing data and kind of being part of the development edge of the community, or I hesitate to say the bleeding edge, but the kind of what's next, I really encourage you to kind of open an issue or just see what's going on at geoconnects.us and look for ways to engage. And then very specifically, if you have data to contribute to the NLDI itself, and would like to kind of become part of that ecosystem, we're really excited to kind of work with all comers and get additional content pulled in. And this is the place to do that. So those two links are in the chat as well. So
yeah, thanks so much, Dave. And I also just want to remind everybody that the presentation will be available as a recording. We'll send it out to all the registrants, and then it'll be posted on the Internet of Water website, along with the slides of the recording. So if you missed the first couple of minutes, fear not, you will be able to find it. And then I also want to encourage everybody to join our P2P network, where you'll get updates about upcoming webinars. And you can get access to our member directory to connect with other water data professionals. And then you can ask questions on our P2P forum and get feedback and share ideas there as well. So thanks so much, Dave, for such a great presentation. I certainly learned a lot. I hope everybody else found it as interesting as I did.
yeah, thanks for coming along. I was really glad to be able to share.
Okay. All right. Bye from now from the Internet of Water and our webinar
See everybody.
series.